Okay, so up until this point, we've talked about kind of the general term for geometric sequences, what geometric sequences are. Now we're going to learn how to solve problems involving geometric sequences. So in example 1, it says find the general term, un, of a geometric sequence knowing that u4 equals 24, so the fourth term equals 24, and u7 equals 192. So when we're talking about general term, when I look at general term for a geometric sequence, what that looks like is un equals u1, the first term, times r, my common ratio, so the number that I multiply by each time to get my next term in the sequence, to the power of n minus 1. So using this information, I can set up two equations for the general term formula. So u4 equals 24. That means that the value of my fourth term is going to be 24. So here's the value, my fourth term here is n, and the value of that term is 24. Simplifying that a little bit, I have 24 equals u1 times r to the power of 3, r cubed. I can do the same thing with u7 equals 192. I have 192 equals u1 times r to the power of 7 minus 1. Simplifying that, I have 192 equals u1 times r to the power of 6. At this point, I have two unknowns, u1, my first term, and r. And I have two equations, which means I can use, this is a system of equations, and I can use substitution or elimination to solve this. I'm going to choose to use substitution this time. I'm going to set each of these equations equal to u1, and then I'm going to set them equal to each other in terms. So I'm solving for u1 in each of these. So to solve for u1 here, I need to get rid of r cubed. So I'm going to divide both sides of the equation by r cubed. So that's going to disappear, cancels out. I have 24 over r cubed equals u1. I'm going to do the same thing over here. So I'm going to divide both sides of my equation by r to the power of 6. So I have 192 over r to the power of 6, and that equals u1 as well. And because these are both terms from the because these are both terms from the same sequence, both of these u1s are equal to each other, which means I can set 24 over r cubed equal to 192 over r to the power of 6 and solve for r. So in order to solve this, I would start by cross multiplying. So I'm going to multiply up here and multiply up here, and that gets rid of our fractions for us. So I have 24 r to the power of 6 equals 192 r cubed. Next, I want to get all the r's on one side of my equation. So I'm going to divide both sides here by r cubed. Those are going to cancel out. Here, when I have the same base and I'm dividing, I can subtract my exponents. So I have r to the power of 6 minus 3, which is 3. So I have 24r cubed equals 192. Solving for r here, I'm dividing both sides by 24. And I'm left with r cubed equals 192 over 24, which is 8. And I know that 2 cubed is equal to 8, so r has to be equal to 2. So I know my common ratio for this sequence is equal to 2. In order to find my first term, or u1, I'm going to plug this value for r back into either one of these original equations. I'm going to choose this one because the numbers are smaller, which means it's probably going to be easier. So plugging that back in, I get 24 over 2 to the power of 3 equals u1. 2 to the power of 3 is 8. 24 divided by 8 is 3. So my first term in the sequence there is going to be 3. So putting all of that together into my final response, it asks me for my general term formula, un. So un is going to be equal to 3 times 2 to the power of n minus 1. And that's your final answer there. Moving ahead, we're going to take a look at a couple of examples of real-world situations, or close to real-world situations. So here, we have a herd of 32 deer, and they're on an island off the coast of Alaska. So we put them on this island, there's no predators, there's nothing there to mess with them, they're just going to multiply. It is estimated that the size of the herd will increase each year by 18%. So this is an exponential growth problem. And this is a geometric sequence here. So I'm looking at UN equals U1 times R to the power of n minus 1. So my U1 here is going to be the first term of my sequence. And in this case, when we're looking at geometric growth, we're looking at the first number that we start with. So we're starting with 32. That's your initial population there. Our R value here is going to be our common ratio. So it's what we're multiplying each term by to get the next term in the sequence. So here, the size of the herd is going to increase each year by 18%. The first thing we want to do is change that percentage to a decimal. So we're going to take that 18 and we're going to divide it by 100. That's going to give me 0.18. If I multiply 32 by 0.18 though, my population is going to get smaller. I'm going to have less deer. And I know that my size of my herd is going to increase. So what I need to remember here is to add 1 to this number, which will give me 1.18. And what that does is ensure that we take into account the fact that we're going to have 100% of our original population and then another 18% on top of that. So when we have exponential increase, our R value here is always going to be greater than 1. So all of that to the power of n minus 1. So when we think about what n is going to be here, we're looking for the value of the herd after 10 years, which is really like saying at the beginning of the 11th year. So this n value here is actually going to be 11. So I have U11 equals 32 times 1.18 to the power of 11 minus 1. Oops. So I have 32 times 1.18 to the power of 10. Plugging that into my calculator here, I have 32 times 1.18 to the power of 10. And that gives me a value of 167.48. There's going to be 167.48 deer. However, it's not really possible to have 0.48, almost half of a deer. So we're going to leave that value as 167. There are 167 deer after 10 years. Part B is asking us how long it's going to take for the herd to reach 10,000. So our UN in this case is 10,000, and you're looking for the n. So we've got 10,000 is equal to 32 times 1.18 to the power of n. This is the number of years that it's going to take the herd to reach 10,000. So in order to solve this, we could use logarithms, but in math studies, we don't do logs. So the best way to do this is on your calculator. What we're going to do is we're going to set up a system of equations, or two graphs here, and we're going to see their intersection point. So in Y1, you're going to enter 10,000. In Y2, you're going to enter the equation here, 32 times 1.18 to the power of n. In this case, we'll call it x. And you're going to press graph. What might happen is you may get a window that looks more like this. This is your default window here. Oops. So what your window will probably look like is this. And as you can see, we can only see a little corner of the graph. We can't see any intersection point between two lines. So we need to readjust our window. And what's important to remember here in this particular problem is when we're looking at our x and y axis. So here's x max, here's x min, here's y max, here's y min. Our y max here, if we're talking about y as our population, has got to be a little bit bigger than 10,000. So maybe we'll make our y max 12,000. When we're talking about x max, we're talking about the number of years it's going to take for the herd to reach 10,000. It took 10 years for the herd to reach only 167. So it's probably going to take quite a few more years for it to reach all the way to 10,000. So we'll make our x max maybe 50. And we're just making an educated guess here. It could be wrong. It could be more time than that, which means we'll have to adjust our window again, but that's fine. When we're talking about x min for time, our time can't be less than 0. We're not going to look back past the original point that we started measuring this population. So our x min is going to be 0. And our y min is our minimum population, so we'll set that as 0 as well. So plugging that into our window here, we have an x max, or an x min, sorry, of 0, an x max of 50, a y min of 0, and a y max of 12,000. Let's take a look at what that looks like. So here's when population is going to equal 10,000. That's our y1. And here's y2, that 32 times 1.18 to the power of x. And what we want is the intersection point. So we're going to go to second function trace, intersect. And we're going to hit enter 3 times. 1, 2, 3. When we do that, we see that y is equal to 10,000, so our population equals 10,000, when x, or our time, is 34.7. So what that says to us now is it is going to take 34.7 years for our population to reach 10,000. So that's an example of exponential growth. Here's an example of exponential decay. So exponential decay occurs when a population, or in this case, a set of members, gets smaller over time. So we're looking at a film club, and we know this is going to be geometric. So we have UN equals U1. U1 in this case is going to be 300 times R. So in this case, we have membership that is decreasing by 6% each year. So if we think about the multiplier here, what we have is 94% of our original membership. And that's our number that we're going to put in here for R. We're going to put 0.94. So if it's decreasing by 6%, what we have left is 94% of that original membership to the power of n. And n in this case is going to be 6. So we're saying U6 equals 300 times 0.94 to the power of 6. And we can plug that right into our calculator here. And that gives me 206.96 members, but you can't have 0.96 of a member of a film club. So we're going to say there are 206 members remaining after 6 years. So this is exponential decay. The membership is getting smaller each year. When we have exponential decay, our R value is always going to be less than 1. So in part B, it's asking us how many years will it take the membership to drop to 150. So in this case, our UN is 150, and what we're looking for is our N value, the number of years. So we are going to do the exact same thing as we did before. In Y1, we're going to enter 150. And in Y2, we're going to enter our equation, 300 times 0.94 to the power of X, or N in this case, the number of years it's going to take for the film club membership to decrease to 150. And we're going to graph that. And you'll see here's our line at 150. And we can't even see our exponential decay graph. That's because our window in this case is way, way, way too big. So when we think about our x-min, we're still talking about years on our x-axis, so it makes sense for our x-min to be 0. Our x-max is probably going to be closer to 10, because after 6 years we had decayed to 206 members. It's not going to take that much longer for us to decay to 150. So maybe we'll put in 15 just to be safe here. Our y-min is talking about our club members. And we can't have negative club members, so we're going to have 0 there for our y-min. And our y-max is going to be the highest number of members that we had. And we know this is an exponential decay, so our highest member is going to be 300, and then we're going to decrease from there. So when I graph that, here is my film club membership at 150 members. And here is my exponential decay graph, and what I'm looking for is the intersection point. So I'm going to second function, trace, intersect, enter, 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 and voila, and my membership is going to equal 150 after 11.2 years. So it will take 11.2 years for my membership to drop to 150 members.